Couple moment, equivalence, and distributed load. Couple moment. A moment of a couple is characterized by two parallel forces of the same magnitude but in opposite directions separated by a perpendicular distance. So here you've got m is equal to f by d, and that's cross multiply. So m0 arises out perpendicular to both of them, and you've got f, and you've got d as well. Now d obviously is the perpendicular distance and r is not. So if you get given r, then you're going to need to work out what d is, and cross multiplication effectively works out perpendicular distance for you. So the moment of a couple can be computed from whatever point as an independent of the point, so hence it is called a free vector. So as with previously, the moment is calculated by m is equal to r of sine theta, or d or fd. Addition of couple moments are analogous to calculating resultant moment from the individual. So mr is equal to the sum of mi, so that's from 1 to n. So what that effectively means is that r times f1 plus f2 plus f3 is equal to r times f1 plus r times f2, etc. And there's a number of couple moments acting on the body. So this is just a more advanced way of saying that. Now note though that moment of couple, so that's couple of forces, is a free vector. The moment of a force or a non-coupled vector requires a definitive point or axis. So remember very clearly this is what you call free vector. So a moment of couple doesn't require a definitive point or axis, whereas a non-coupled force would. So equivalent couples, it involves two couples of which the moment m are equivalent. So that is the same effect on the given body. So for example here, okay, I've got a hand that's spinning it. So I'm pushing 30 newtons there, and it's divided by 0.4 meters. So if you multiply, it's 12 newton meters. Here on the other hand, 40 newtons and 0.3 meters, and it's 12 newton meters. So these are both exactly the same. However, it involves two different couples altogether. Equivalent force system. So equivalent systems is based on the concept of equivalency. So that's two sets of loadings are equivalent if they produce the same effect or motion on a body, and two sets of loadings are equivalent if the resultant forces or moments are same in the equivalent system. So that is that the sum of the forces before is equal to the sum of the equivalent, or the sum of the moment before is equal to the sum of the equivalent moments. The reason why we need to find the reduction of a force couple system is that equivalent systems provide a way to simplify a problem. So to find an equivalent system, replace the force applied at a point with another force, remembering both systems have to have the same resultant force or moments. So for example, equivalent loading at point O. Where point O is on the line of the force, so as you can see here, it's on the line, then you can just simply add an equal and opposite, so one there, and you cancel those two out, which effectively gives you that one. So that's on O. So remember how before it wasn't on O, now it's on O. So effectively just moving it back. I'm just doing it the more difficult way. However, where the point of O is outside the line of force of actions are here, F, and O is over there. Yes, you can put one here and one there. However, even though you're going to cancel to get that, what's going to happen effectively is you're going to create what you call a moment. So this generates a moment. And you can just think about that very carefully, basically, because if the origin or the axis is here, if you were to push that, it's going to spin, right? So therefore it's creating a moment. It's quite obvious. And distance obviously is going to be here D, which is just there. The equivalent loading of several forces, so here you've got R1, F1, R1, F1, R1, F1. You can all add them up together, and you can find the equivalent moment as well. So that's where the force before is equal to the force after, so that's the force of the additions. The previous moment is equal to the previous moment of the equivalent system. So as a quantitative example here, I want to show you this one. You've got the red line going down there, and that's 30 degrees, which effectively means that it's 30 degrees there because it's an alternate angle. And then you've got this one, which is just going up there with 200 newtons. This one's 450 newtons. Now, first of all, you got to understand, basically, we want to shift this one down to the origin, and we want to shift this one to the origin as well. We can find what x is then for that one. So as you know, sine theta, so sine 30 is equal to opposite over hypotenuse of x over 450. So sine 30 is equal to x over 450. Therefore, x is equal to 450 sine 30, which is equal to 225 newtons. On the other hand, cos 30 is equal to adjacent, so y over 450, and therefore y is equal to 450 cos 30, which is equal to 389.7 newtons. So we effectively now know that this component is 389.7 newtons, and this component on the x-axis is 225 newtons. Now let's assign directions. So this will be positive, going that direction will be positive, and going down will also be positive as well. So if we have a look here, going down is going to be positive, and therefore that's going to be, the y is going to be positive, and going across is going that way, and so therefore that one is going to be negative. And also know that this one, on the other hand, the x component here is 0, and the y component is 200, which is going up, and therefore it's going to be minus 200. Now here, 0, you can also write minus 225, which is going to give you 225 newtons. Now that, because it's minus, it's going that way. So it's going this way. Ry, on the other hand, is going to equal 389.7, so that's the y component of that, minus 200 because it's going the opposite direction, and that will give you 189.7. And because it's positive, that will be going down. Because we've got the x and the y components, we can now find what r is, because r is equal to x, so this is Pythagoras, rx squared plus ry squared, square root of that, which is going to give you 294 newtons. So m0 is equal to fd, and therefore we know that minus 225, because it's going that way, is going to be multiplied by 0.2. Because remember, minus 225 newtons is the amount of push this way. So it's the amount of push going left. And therefore, we want to find the perpendicular distance to that, which is going to be right here. So therefore, minus 225 multiplied by 0.2. On the other hand, 389.7 multiplied by 1.5. The reason for that is that's the y component there. And you want to multiply that by 1.5, which is there. Because remember, this is a y component there. And that's the perpendicular distance. And then you want to minus 200 multiplied by 3.5. And the reason for the minus is that because it's going up in the opposite direction. And 3.5 is the perpendicular distance, which is just there. And the other one you want to do is add on to 200. The reason is because of that. Because if this is going positive and that is going positive, therefore going this way is going to be positive. And therefore you add on 200. And the effective sum is going to be 39.55 Newton meters. I mean, because it's positive, it's going to be in the direction as you assigned. And we assign clockwise as being positive. And therefore that's positive as well. So what we've effectively done there is we've used everything that's up here. So we've used the 225, we've used the 389, we've used the 200 newtons, and we've used the 200 Newton meters there. However, here, because we want to find the equivalency, we're going to have to use r instead, so this stuff that we found down here. So as you can see, we've resolved it into its x and y components. So minus 225 multiplied by 0.2. Because even at that original point, there's going to be a distance of 0.2 with the center. On the other hand, plus 189.7, which is that. We multiply that by d because we're trying to work out what the equivalent perpendicular distance is. And that must equal 339.55 Newton meters as we've decided there. And therefore, if you reshuffle that around, you'll find that this d has to be 0.4457 meters. Distributed load. Distributed load involves the assumption of a very large body area that is subjected to external forces, or otherwise known as loading. It is assumed that the shape of the body is flat and rectangular. Now, an example of distributed load, for instance, is a wind coming up against a building or hydrostatic forces on a submarine. Now, simple distributed loading is what we're going to be doing, is a calculation of intensity given by force per length. So that's newtons per meter, force per length, or area, which is force per area. So that's newtons per meter squared. Because length is counted in meters and area is calculated in meters squared and force is n. Now, the intensity of loading or force is uniform along the affected area. So that's the assumption that we made of uniformity. The characteristic of simple distributed loading is an infinite number of non-overlapped parallel forces. And the reason why there's infinite number is because it needs to be uniform. And the reason why it's non-overlapped is because if it overlaps, then they're going to interfere with one another. Now, it is a coplanar force system if distributed is along one axis. So as you can see that it's just along one plane. On the other hand, a parallel force system, the load distribution is along two axes. So as you can see that it's coming all around there. Now, in a distributed load problem, instead of finding individual forces, we replace the whole distributed load with a single force. So you can see there's infinitely many that are non-overlapping, non-overcrossing, that are parallel, and we replace it with the one like that. And it's going to be at the center point of all of that. Now, the magnitude of the resultant forces is a summation of all forces applied on the surface. The intensity of loading is proportional with the size of the area length. So in other words, Fr, so the resultant force is going to equal Wa, and Fr is going to equal Wl. So Wa, W being the intensity, and A being the area, or L being the length. Because remember, W is intensity, and this is effectively Fr over A, which is effectively force per area, or Fr over L, which is effectively force per length. Now, the location of the resultant force, that is the line of action of Fr, is through the geometric center or the centroid of the affected area. Now, for example, we've got here, between A and B, that's 1.5 kilonewtons per meter, and that's for 3 meters, 1 kilonewtons per meter, and that's 3 meters, and that's 2.5 kilonewtons per meter for 1.5 meters. So first of all, we're going to assign that as F1, F2, F3, we're going to assign going down as being positive. So F1 is going to equal 1.5 multiplied by 3, because it's just those two together. So it's W times L, and that's 1.3 times 3, which is 4.5 kilonewtons. On the other hand, for F2, it's going to be 1 times 3, which is going to equal 3 kilonewtons. And then we've got 2.5 times 1.5, which is going to give you 3.75 kilonewtons. Now, Fi is going to equal F1 plus F2 plus F3, and because they're all going downwards in the positive direction, it's going to be 4.5 plus 3 plus 3.75, which is 11.25 kilonewtons. Now, that was the easy part, adding them all together. The hard part is going to be the calculating of centroids. So X1 is going to equal, so the centroid of this one is going to be the center of this. So x1 is going to equal 3 over 2. And the reason for that is that this distance is going to equal 3, and therefore you get 3 divided by 2. So the reason why that's 3 plus 3 over 2 is that this is obviously 3, and because this one is also 3, you get divided that by 2, so 3 over 2. Now for the last one, it's going to be 3 plus 1.5 over 2, and that's because you have 3 plus 3, those two, so you've got that distance now, plus 1.5 over 2, because it's 1.5 is that distance, and you want to divide that by 2, so you get effectively that distance there. And that gives 6.75 meters. Now therefore, you can use m0 equals fd, and that's why you can get 11.25 d, because we want to find the effective centroid, and we don't know that, is equal to 4.5 multiplied by 1.5, 3 multiplied by 4.5, plus 3.75 multiplied by 6.75, and therefore you can find d is equal to 4.05 meters.